In this lesson, we're going to be looking at some of the properties of polynomial functions. We're going to be looking at how to graph a polynomial function, as well as how to come up with the equation of an existing graph. And we're also going to be talking about the concept of odd and even functions. So there's going to be a lot in this lesson. I would encourage you to go through it carefully and maybe even listen to this one twice. There is a lot of new material, new information here, and it's not that it's particularly difficult, but just that there's many new concepts that I want to make sure you understand. So we're going to start by looking at graphing polynomial functions. A couple of things I need you to remember here at the beginning. First one is when we talk about the roots of a polynomial equation, that corresponds with the zeros of the function and the x-intercepts of the graph. So sometimes we use those words somewhat interchangeably. They are not all exactly the same thing, but they do have the same value. So if, for example, the parabola with the equation y equals -2 times x plus 4 times x minus 3 has x-intercepts at -4 and 3, because those are the zeros of this corresponding equation. Those are the values of x that if I replace x in the equation with those numbers, then the value of my function is going to be 0, which is why there's x-intercepts at those points. So the x-intercepts are at -4 and 3. This is true for all polynomial functions regardless of their degree. So in the next example here, we are looking at the graph of y equals 1/2 times x plus 2 times x minus 1 times x minus 5. Note that the graph beside shows you that the x-intercepts are at -2, 1, and 5. So don't forget that the sign on the x-intercept is actually opposite to what it is in brackets. So your x-intercepts are at -2, +1, and +5. Next, we want to look at the behavior of different polynomial functions at each intercept, because that's going to allow us to be able to graph a polynomial function from its equation. We notice that when we're talking about polynomial functions, these graphs don't always behave the same way at their intercepts. So when we, just to tell you what I mean by that, when we learned about parabolas, remember that a parabola, if I could just make a quick sketch for you here, sometimes your parabola crossed directly through its intercepts, like that. And other times you had a parabola that had its vertex right on the x-axis. So at its intercept, let me grab the other color, sorry. At its intercept, it sort of touched down to the axis and went back up. So polynomial functions behave similarly in that the behavior of the function is not always the same at its intercept. So let's look at how each of the next three graphs behave at the intercepts and see if we can find a pattern. So notice in these three graphs, in some cases, your graph does pass directly through its intercept, sort of in a straight line fashion, like here and here in the third one. Okay, in other cases, notice that your graph approaches its intercept and then goes back in the same direction, sort of like a parabola. So at that one, or this one, or this one, or this one. Okay, and in the last example, you also have this strange sort of pattern at the last intercept where your graph sort of curves down towards the intercept and then curves down in the other direction, sort of like the shape of a cubic graph. Now let's have a look at the equations for these functions. So for example, all of the, let's have a look at the intercepts that I've marked off in red. So for example, your first graph has an x-intercept at -4. The middle one has x-intercepts at -2 and 3, and the third one has an intercept at -3. And the graphs behave the same way at all of these intercepts. If you look at the factors that correspond with those intercepts in the equation, you will notice that they have something in common. So I'm circling the factors that go with all of those intercepts. And what you should notice is that in each case, the exponent on that factor is 2. Now, have a look at the intercepts that pass directly, the intercepts where the graph passes directly through the intercept. So that would be in your first graph at 1 and on your last graph at 0. If we look in the equations for the factor corresponding with those intercepts, we'll notice they also have something in common. And that is the fact that the exponent on each of those factors is 1. Even though the exponent's not written, the exponent is actually 1. And finally, for the last case, you will notice where, for your last graph, where your x-intercept is 2, have a look at the equation, and the exponent on that factor is 3. So it turns out that the exponent on the factor in the equation has a lot to do with how the graph will behave at that particular point. Now there's a name we give to that exponent. Okay, we call that the order of the root. So we're going to make a side note here that says the order of the root is equal to the exponent on the corresponding factor. Okay, and in this table we're going to summarize how the graph will behave at each particular root depending on what the order of that root is. So under order of the root, I notice I've used the word single, double, triple. When the order of the root is 1, we generally call that a single root. When the order is 2, we call that a double root. And when the order is 3, we call that a triple root. So for your single roots, those were the ones I had marked off in blue in the previous 3 examples. Notice your graph will always sort of pass directly through the root, as we said, in sort of a straight line fashion. So over here we're going to make a side note. If you have a single root, you're going to think of a line. In other words, a function with a degree of 1. Okay, you're going to think of the line. If your root is a double root, so the order of the root is 2, then those were the ones we marked off with red in your previous example. They were the ones that behave a little bit like a parabola at the root. And so when we're dealing with a double root, we're going to think of a parabola. So if the order of the root is 2, think of a function with degree 2, which is the parabola. And finally, if your root is triple, it behaves like a cubic function, like the graph of y equals x cubed, which curves either up like that, or if you're approaching it from the other direction, it's going to curve down like that. So you're going to think of a cubic function. Now, cubic functions are kind of new this year, okay, so you're not as familiar with that one, but that is what the cubic function behaves like. It curves up and goes in the other direction. Okay, from here, we are going to now look at how to put some of this information all together and create the graphs of a few polynomial functions. So let's start with this first one. Looking at the first equation, we can see that we have roots at -2 and 5. And I'm going to look at the exponent on each of those factors to determine the order of each root. So the exponent on my first factor, which corresponds to the intercept of -2, is a 1. So I know that that is a single root. And the exponent on the other factor corresponding with my x-intercept at 5 is 2, which means this is a double root. So that's going to tell me something about how the graph behaves at each of those roots. The degree of this function is 3. 2 plus 1 is 3. So this is a cubic function with a positive leading coefficient. The leading coefficient here is actually 1. So this is a cubic positive function. Therefore, I know that the end behavior of this function is q3 to q1. So the overall behavior of this graph is it will originate somewhere in quadrant 3, and it will travel to somewhere in quadrant 1. Let's mark off the roots at -2 and 5. Okay, and it can also be helpful for you to find the y-intercept. So to find the y-intercept, we're going to let x equals 0 in the equation. Okay, and if we solve that, we can see that the y-intercept is 50. So we'll mark that off right here, assuming each square is 10. We'll say that that is 50. Now, using the order of the root to get started here, we know that -2 is a single root, and we know that the end behavior starts here in quadrant 3. So that means the behavior at this root is going to be sort of linear like that. It's going to go straight through at -2. Whereas on the other side, this is a double root, so I know my graph is going to behave like a parabola. And I know it's above the axis because the end behavior continues on in quadrant 1. So now in the middle, we're going to go through the y-intercept, back down, and there we have our polynomial function. Notice the y-intercept is not a maximum point in this particular question. Since the y-intercept is a little closer to the root at -2 than it is at 5, we know that the maximum point would be a little closer to halfway between those roots. Not necessarily exactly, okay? We don't have to worry about the exact height of that maximum point, but we do need to make sure we know that the maximum point in this case is not necessarily at the y-intercept. Okay, let's have a look at the next example. Your next one has roots at -3 and 1. The root at -3 is a double root, and the root at 1 is also a double root, coming from the fact that the exponent on each factor is 2. So we've got roots at -3 and +1. This is a quartic function, so the degree is 4. Okay, and again, your leading coefficient is positive. So we're going to call this a quartic positive function. So that means the end behavior goes from quadrant 2 to quadrant 1, similar to a parabola with a positive leading coefficient. And my y-intercept, if I replace x with 0 in the equation, I can see that my y-intercept is at 9. So we're going to mark that off on our graph as well. Okay, so we'll mark off our intercepts. There we go. Now our end behavior is quadrant 2 to quadrant 1. Okay, so this graph is going to originate somewhere in quadrant 2, travel through its roots, its intercepts, and end up in quadrant 1. This is a quartic function, and both roots are double roots, which means that our graph behaves like a parabola at each of those roots. Now, it's going to travel up through its intercept. I did not hit the intercept. It's very difficult with this app to do that, but it should go directly through the intercept, okay? Kind of like that. So a little bit like a W. And once again, the maximum point is going to be just to the left of the y-intercept, okay? The y-intercept is not right in the middle of the two roots, so therefore the maximum point won't be either. In fact, I probably could have drawn that to highlight that a little bit better. Okay, so your maximum point would be kind of more over on this side, and then your y-intercept is at 9. Forgive me for the terrible graph. This app makes this very difficult, so hopefully you can see what I'm trying to accomplish there, and if not, make sure you ask me and I'll clear it up for you. So at this point, could you head over to video 2 and we'll finish this example and go on to the next one.